Welcome to our video for Stat 333. This is an overview of the MLE, which is maximum likelihood estimation, and MME, which is method of moments estimation section. So in this section, we're going to learn how to find the maximum likelihood estimator, which is MLE, for a population parameter. We want to be able to find a method of moments estimator, that's an MME, of a population parameter, or of a distribution parameter, however you want to call it. We want to be able to determine the bias of an estimator, the mean square error, so mean square error, or MSE of an estimator. And we're saying an estimator, so this is a statistic. These estimators are statistics. They're calculated from data. If we have a sample, they're calculated from a random sample or a sample, depending on the sampling method. We also want to understand the proofs and be able to apply those methods or steps in the proofs to problems, and we want to be able to apply the methods to new problems. So that is what we're going to cover in this section. Now, let's get started, but before we do, let's do some review. So we need to review some things that we learned last semester in order to be able to handle this material easily. So we're going to let x and y and x1, x2 up to xn, all of those are going to denote random variables. And so A is going to be a real number, that means it's a constant. B is a real number, and then we're going to do a sequence of these real numbers or constants, A1, A2 up to AN. And so these are real numbers or real constants. Okay, so we have a constant times a random variable plus a constant. We want to take the expectation, right? So these are properties that we studied and that you need to know. So hopefully they're on your formula sheet. So we have E, so this is a linear operator, so we can distribute the expectation across this. So we'll have EAX plus E of B. Now, the expectation of a constant times a random variable, we can pull the constant out so that we end up with A times EX plus B. The expectation of a constant, there's no randomness in a constant, so it's expected value or expectation, or average if you want to think of it that way, is just itself. So this is the answer. Let's do the same thing with variance, but now we have to remember that the variance is covariance. So if we wanted to prove this, we could break this down as the covariance of AX plus B with itself. That's the definition of variance. And then we could work through this. I'm not going to go through that because we've already proved that last semester, but I am going to work through the, I'm going to show we've proved this property before. So this is going to be the variance of AX plus 2 times the covariance of AX with B plus the variance of B. Well, the covariance of anything with a constant, and B is a constant, is 0. So that's 0. And the variance of a constant is simply the covariance of a constant with itself. That's going to be 0. And then if you remember that the variance of AX is going to be the covariance of AX with itself. And so every time we have a constant, we have to pull it out. So we have it twice here. So we end up with A squared. Covariance of X with X is, by definition, the variance of X. So this is A squared times the variance of X. This is a linear operator, as we mentioned. So for 3a, this is simply going to be A times E of X plus B times E of Y. Okay? And then we have the variance here. This is going to be AX, and we did not say that these are independent, right? And since we did not say that X and Y are independent, we have to write this as the variance of AX plus 2 times the covariance of AX BY, it's supposed to be a Y, plus the variance of BY, and this is going to be, so I pull out the square of this, so A squared variance of X plus 2AB covariance of X with Y plus the variance of BY, that's going to be B squared variance of Y. So I hope this is familiar with you, to you, and that it's very easy for you to do this and you remember it from last semester. Okay, now the variance of AX plus BY when X and Y are independent. This symbol means X is independent to or orthogonal if we're talking about matrices, or at right angles if there's if you want to think about it that way in two-dimensional space. So X and Y are independent. That means that the covariance of X and Y here, because you notice this is this and this are the same, well, now the covariance is going to be 0. So we're going to end up with A squared variance of X plus B squared variance of Y, because the covariance between X and Y is 0 when X and Y are independent. There is no dependence or codependence between the two variables. All right? If this does not make sense to you, please go back and review this, or you can ask me in office hours. I will work through more detailed explanations. Okay. Now, I should probably review the expectation is equal to one of two things. It's going to be the sum of cross X of X times the PDF of X, or if this is discrete, if X is discrete, if X is continuous, we'll have the integral across X of X times f of X dx. This is when X is continuous. But it doesn't matter if X is continuous or discrete. These properties that we're working out down here, they apply regardless. In fact, all the way through this section. Now, I said that the expectation was a linear operator, so now I've got this linear function of x1, x2, or linear combination of x sub I times a sub I. So this simply turns out we distribute the expectation across the summation, and we end up with a1 e of x1 plus a2 e, of x2 plus dot 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 plus an of e of xn, the expectation of xn. Okay. Now, if x1, x2 up to xn are pairwise independent, then we can do the following. And so if we have a random sample, then this is true, that x sub 1, x sub 2, up to x sub n, they're all pairwise independent because they are independent and identically distributed random variables if they're from a random sample. And that's mostly what we're going to be dealing with this semester. Okay, so I have a1, x1. Well, when they're independent, pairwise independent, if you remember what this would turn out to be, would be the variance of a1, x1 plus the variance of a2, x2 plus the variance of an, xn plus then the covariance of a1, x1, a2, x2, and all these possible pairs of covariance. Covariance of, we'd get to a n minus 1, xn minus 1, an, xn, comma. So the covariance of this. All these covariances go to 0 because the random variables are pairwise independent. So this is going to equal the variance of A1 x1, that's going to be A1 squared, variance of x1, plus A2 squared, variance of x2, plus dot dot dot, for each of these up to an squared, variance of x sub n. Okay, so when we have independence, the variance of the linear combination is very simple compared to when we do not, because all of these covariances, and remember that covariance is related to correlation, so if random variables are independent, then the correlation is 0. It doesn't work the other way. Correlation of 0 does not say that the random variables are independent unless they are normally distributed. So that's a special case. So we say that x1, x2, up to xn are IID, independent and identically distributed, if x1, x2, up to xn are pairwise, independent, and x1, x2, up to xn have the same or a same PDF or PMF if they're discrete. So, if we have a common PDF for all these variables, so x sub I equals 1 up to n, let's say, then each xi has the same mean. It has the same, it has a common PDF, so that means they're going to have the same mean, and they're going to have the same variance. In fact, they're going to have all the same properties. Okay. Now, as I said before, random sample, and that's what this abbreviation stands for, in case you don't remember or in case you're visiting. So we say that x1, x2, up to xn is a random sample of size n, because there's n of them, from a population with PDF or PMF, from a population with a PDF or a PMF, the same PDF or PMF, if x1, x2, xn are independent. Okay. The population mean, mu, equals E of xi, and again, if it's discrete, then we have to use the summation form of the expectation, which is the sum of x times f of x, for x from negative infinity to positive infinity. Remember, it's discrete, so we can set x from negative infinity to positive infinity. If x is continuous, then we have to use an integral. So it's x f of x, now dx, and the integral from, again, negative infinity to positive infinity. Remember that x, you'll reduce this from negative infinity to positive infinity. You may reduce it depending on the support of x, what values of x, f of x, is greater than or equal to 0. Okay? And then the population variance is the variance of xi. And again, for the discrete, we have the sum of x minus mu, quantity squared, times f of x. And remember, there's a shortcut formula that we'll review here, I hope, soon. That's if x is discrete. If it's not discrete, then it's the same formula, x minus mu squared f of x, but dx, and it's an integral. Okay? That's for continuous. A joint PMF or PDF. If x1 to xn are pairwise independent random variables with PMFs or PDFs, f sub I of x. In other words, they don't necessarily have, they're independent, but they are not identical. They may have different PDFs or PMFs. And so f sub I of x is the PMF of the ith random variable. I goes from 1 to n. Then the joint PMF or PDF, we'll call it G, of x1, x2, up to xn, is simply the product of f sub 1x times f sub 2x times f sub 3x, all the way up to however many there are, whatever n is. That can be written in this notation. This pi symbol, large pi symbol, is a product. So from I equals 1 up to n, we're going to multiply each of these PDFs or PMFs, f sub I of x. Okay? And remember, so f sub 1 of x is the PMF or PDF of x1. And f sub n of x is the PDF or PMF of x sub n. Okay? Now, the joint PMF or PDF of n random variables is required to be a function of those n random variables. So this is something, these are some properties, okay? So that function can be 1. So you might say that the random variable, the joint PMF or joint PDF of these n random variables is f of x1, or actually we used g, didn't we? So we'll use g here. G of x1, x2, up to xn. It could simply be x sub 2. And all the other functions could just be the identity times 1. So that could be the case. Okay. So don't let this mess you up with the saying that it's a function of all n random variables. Remember that a function of one random variable could be the identity 1. Okay. So if x sub 1 up to x sub n are IID, independent and identically distributed, with a common, they're going to have a common PMF or a common PDF, so I don't need to index it if they're all the same. It can just be written as f sub x, f of x. Then the joint PMF or PDF is written as the product of these, okay? So it's just the product of those PDFs or those PMFs, all right? And you'll notice that I'd still use x1, x2, and xn. I still denote them, even though they're independent, okay? All right. Now let's talk about the standardized form of a random variable, x. So the standardized form of a random variable x with mean mu equals e of x and variance sigma squared equals variance of x is given by x, this is a capital X, minus mu over sigma. Okay, so that's the standardized form. Now, the mean of this is mu of z is equal to e of z, which is equal to e of x minus mu over sigma. Remember, sigma is a constant, so it's going to come out, and I'm going to have 1 over sigma, e of x minus mu, and then I can distribute the e, which is 1 over sigma, so I'll have times e of x minus e of mu, but mu is a constant. So this is going to equal 1 over sigma, e of x minus mu, but e of x is the mean of x is mu. We've already said that. So that's 1 over sigma, mu minus mu. This is 0, so this is 0. So it doesn't matter what distribution x comes from, the standardized form has a mean of 0. Now, let's look at the variance of z. So this is going to be the variance of x minus mu over sigma equals, now this is a constant, so I'm pulling it out, but when I pull it out for the variance, I have to square it. 1 over sigma squared, the variance of x minus mu. Okay? Well, by definition, the variance of x minus mu is equal to sigma squared. So this is 1 over sigma squared times sigma squared. So this is sigma squared over sigma squared equals 1. So the variance of a standardized random variable is always 1, and the mean is always 0. Okay. Let's do an example. Let's suppose that a random sample of n equals 36 families are selected from the following population. 10% of the families have no children or 0 children. 20% have 1 child, 40% have 2 children, and 30% have 3 children. We add this up, 30, 70, 80, 90, 100. So this is 100% or total. So out of this population, we're going to say that this is the distribution. Okay? So we have a discrete distribution here because what's the random variable? X is the number of children in the n equals 36 families. Okay, so the number of children is the random variable. We want to find the population mean and variance, the PDF of each x sub I, and the mean and variance of each x sub I. So the population mean and variance is for this random sample, right? Okay, so remember that the mean is equal to the expected value of, in this case, x, which is going to be, since it's discrete, the sum of little x times f of x. Now, what is f of x? So I can put x and f of x. I can do that this way, maybe. So we have 0 children, 1 child, 2 child, and 3 children, or 2 children, 3 children. Okay, so using this as the estimate of the probability, we would have 0.1, 0.2, 0.4, and 0.3. Okay, and if we add these up, we get 1.00, or 100%. So remember that x times f of x is going to be x equals 0 to x equals 3. And so it's easy to do this in a table form. So 0 times 0.1 is 0. 1 times 0.2 is 0.2. 2 times 0.4 is 0.8. 3 times 0.3 is 0.9. We add these up, 17, 18, 19. So 1.90 equals the sum of x times f of x, which is equal to mu. So this is going to be, you could write this out as 0 times 0.1 plus 1 times 0.2 plus 2 times 0.4, if you wanted, plus 0.3 times 0.3, or you can use the table here to do this a lot quicker if you're doing it manually. And so this is going to equal 1.90. So the mean is 1.90 children. So we also, so this is I, and we also want the variance, the population variance. So the variance of x is going to equal sigma squared, that is E of x squared minus mu squared. That's another way of writing this, or EX quantity squared. That's mu squared, right? So we've got mu squared. So we've got x, mu, or E of x. Let's see if we can, let's get our, that's a little big, isn't it? Oh, no, that's all I got. All right. So that's 1.9. Now, what we'll do is we'll do x squared f of x. Why? Because E of x squared is equal to the sum of x squared f of x. All right. So x squared, I've already got x times f of x here. If I multiply that by x, then that is x squared f of x. So I'm going to take the 0 times the 0, that gives me a 0. I'm going to take the 1 times the 0.2, that's going to give me 0.2. I'm going to take the 2 times the 0.8, 1.6. 3 times 0.9 is 2.7. I add these up, and I get, let's see, 4.5, it looks like. If I did that right. So 13, 14, 15, yeah, 15, 1, yeah, 4. Okay. So now, this is E of x squared. So this is going to be 4.5 minus mu squared, 1.90 quantity squared. I use my calculator real quickly, and we will do 4.5 minus 1.9 squared equals 0.89. This is the variance, the population variance. So let's do this second part. And so 2, we want the PDF of each x sub I. So what we have is we have f of x sub I equals 0.1, comma, if x sub I equals 0, 0.2 if x sub I equals 1, 0.4 if x sub I equals 2, and 0.3 if x sub I equals 3. Okay, so that's the PDF there. All right, now let's look at example B. So we have x1, x2 to xn are IID random variables, independent and identically distributed, with a Poisson distribution, and therefore the PDF is f of x equals mu to the x e to the negative mu over x factorial. X can be 0, 1, 2, 3, etc. It says find the joint PDF of x1, x2 up to xn. So g of x1, x2 up to xn is equal to f of x1 times f of x2, oops, it's supposed to be a 2, times dot 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 f of xn. And remember that we have, so mu, oops, mu of and raised to x1 e to the negative mu. They all have the same mean. And then we have x1 factorial times mu raised to the x2 e to the negative mu, x2 factorial, mu raised to the xn e to the negative mu, x2 xn factorial. And so I have mu raised to the x1 times mu raised to the x2 times dot 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 mu raised to the xn. This is going to equal mu to the sum raised to the sum of the xi. Okay, xi equals 1 to n. And then I have e to the negative mu times e to the negative mu times e to the negative mu, so forth, n times. So when I sum those exponents, I get e to the negative n times mu. There's n of them. I have mu, and there's n of these. So there's n times mu. All right. And then, oops, come back from erasing, back to here. And then I'll have x1 factorial, x2 factorial times all the way up to xn factorial. And then we will say, so this is going to be the joint PDF, and we have to say xi equals 0, 1, and so forth for I equals 1, 2, up to n. Don't forget your support of x. Okay. So that is the review, and we will stop here for this first video. So this first video has been a little long, but that's because I wanted to get through this review section all in one sitting. Okay, we'll see you in the next video. Take care.